Section 2.4 is really going to center around one little topic, and that is the average rate of change of a function. And really the average rate of change is the slope of a line between 2 points. Average rate of change of a function. Like I said, that's going to be the slope of a line between 2 points. Now, we've already dealt with net change in a function a couple times. Let's look at the average rate of change for problem number 8. Now, this one's not too bad to do visually, at least as far as the net change is concerned. How much of a change is there as we move from this point to this point? What's the net change in the function? 2. Is it going to be a positive 2 or a negative 2? Negative 2. Yeah, you're going down by 2. So you subtract 2 here minus 4 here. You get a net change of negative 2. Net change. So that's the net change. But if we divide that by the length of this interval, which is 4, then the average rate of change is really just the slope. So the slope is going to be the rise, which is negative 2, over the run, which is 4. So the average rate of change is negative 1/2. Now we're calling it the average rate of change because that's what happens when you add up and divide for all these changes. The function actually starts out by increasing, right? It's increasing for a little while, then it slows down, then here it kind of stops, and then it starts decreasing. But on average, average rate of change is negative 1/2. Let's apply this to a couple of problems in the book. And again, if you've taken time to pull up your email and look at Desmos, we're going to look at problem number 12. Now I've programmed problem number 12 in for us on Desmos, so let's take advantage of that. Here's our function. You can always click projector mode to make that a little bit more solid of a grid. And they're going to ask us for the average rate of change in this function between 3 and 6. So let me write that down here for us. So let me go back here. Problem 12. They call it R of t. Let's zoom out a little bit. There we go. R of t is 3 minus 1/3 t. And I want the average rate of change between t equals 3 and t equals 6. Now, when I programmed it into Desmos, I used x's and y's instead of t's and r's, but it amounts to the same thing. You could think of it this way, of t and r, 3 and 6, and just want to find the y coordinates here and find the slope of the line. Let's do it on Desmos and see if we can't get a little bit more insight into it in terms of its graph and some of the geometry. So let's turn on some of these points. If you plug in an x equals 3, or in the case of the problem, a t equals 3, you get back that r equals 2. If you plug in 6 for x, you'll get back 1 for y. So we get those 2 points. We want to find the rate of change between those 2 points. Let me kind of zoom in. There you go. So you can kind of play around and figure that out. Let's do it over here. So the slope of the line is going to be 1 minus 2 over 6 minus 3. So we get negative 1/3 as our average rate of change. And that kind of makes sense in another way, right? Does anyone else see something interesting about 1/3? That's the slope of our line, right? It's just negative 1/3. So it makes sense. In fact, do you think our average rate of change would be different if I chose a different point? What if I chose 9 and 0? Is that going to change my average rate of change? No. Your average rate of change for this line is going to be stuck at negative 1/3 no matter where you're at, no matter what 2 points you choose. So kind of nice to be able to look at the graph on that one. Let's ditch this one and look at the next one. Problem number 20. So let's come over here. This time our function looks like f of x is 1 minus 3x squared. And we want to find the average rate of change between 2 and 2 plus h. 2 and 2 plus h. Well, this is going to look like your divided difference type problem. So let's see if we can't figure out what's going on with that. So I'll plug in some values into my function and see if we can't simplify that a little bit. So x and f of x. If x is 2, what is f of 2 going to equal? One minus 3 times 2 squared. Anyone before I get done? Negative 11. Good. So 1 minus 12 is negative 11. So that's f of 2. What about 2 plus h? Well, that one's going to be a little bit more work here to plug this one in. Let's get rid of you. There you go. So f of 2 plus h is going to be 1 minus 3 times 2 plus h squared. It's helpful if you can square that out in your head. Remember, you're going to get the n terms squared. So 4 and an h squared. So yeah, the n term squared. And the middle term, I'm not sure if Lisa's voice picked up on the microphone here, but it's going to be 2 times 2 is 4 times h. So plus 4h plus h squared. Almost done. Let's clean this up a little bit. If I distribute that, I get 1 minus 12 minus 12h minus 3h squared. All right. So kind of a messy expression here, but that's our f of 2 plus h. Right there. F of 2 plus h. Keep in mind, I want to find the slope of the line between these 2 points. So the slope of a line is going to be y2 minus y1 over x2 minus x1. So I got to subtract the y coordinates over the difference in the x coordinates. So the difference in the y coordinates is going to be 1 minus 12. Actually, I should have probably just put that as minus 11, right? Minus 11 minus 12 h minus 3h squared. So minus 12h minus 3h squared minus, so that's my y2, minus what? Negative 11. Over x2, which is 2 plus h, minus 2. we're going to get some nice cancellation here. That's negative 11, and that cancels out with that. What other cancellation can I do in this one? 2 and 2 cancel in the denominator. So what am I left with? I'm left with minus 12h minus 3h squared over h. You should have seen this kind of stuff before. And yeah, we can get the h out. So thank you. So I'll factor out the h. Now I could factor out the negative 3 and the h, but I'm only going to get cancellation with the h. So let me just factor out the h. H times negative 12 minus 3h over h. And that last little bit's going to cancel. And I'll get negative 12 minus 3h. Yay. So that's your final answer there. That's the average rate of change. Now it depends on how big h is as to how much your average rate of change is. You're just looking at the slope of a line between these 2 points. I did a lot of calculation here. Really, this should look a lot like your divided difference stuff that we did a little while ago. So, are our calculations okay? That's a yay. Let's look at it graphically and just understand briefly what's going on graphically. And I'm not really going to hold you responsible for much off of this graph, but let me turn on this one. And let's see. My window settings, I'm going to use these recommended ones up here. So 0 to 6 on the x-axis and negative 60 to 0 on the y-axis. Here's my point at 2 and negative 11. And if I turn on another point, say this one, I can look at the line between these 2 points. And the slope of the line is going to be my average rate of change. So let's see. I want to turn on the line there. Now watch what happens as I let h get smaller and smaller. The slope is going to get, or the line is going to get closer and closer and closer to that point. So, wow, you can get really, really close. And eventually, what's going to happen is you're going to get something called the instantaneous rate of change. But that's for a different course, not this one. Okay. A couple more to finish up rate of change. Let's take a look at problem 28. It says graphs of f, g, and h are shown below. What can you say about the average rate of change of a function on each of the successive intervals? Let's start out with one that we've already practiced. This one. What's happening with the average rate of change on that one? Or what is the average rate of change? The slope. Good. And what's the slope of this line? Well, let's just pick a couple points. Let's see. That looks like that's 0 and 1, so that's 2. You know, it doesn't look too friendly. Initially, I thought it was going to be a slope of 1 because of the way this is, but the x-axis is scaled differently than the y-axis. So, yeah, it's whatever the slope of this line is, it's constant throughout the function. But do I have a constant slope in the second one of these for G? No. It starts out, the average rate of change is kind of slow. I mean, it's a slow growing function until around here. Then the function kind of takes off. Reminds me of the graph of an exponential function. That is, at some point, exponential functions grow really, really quickly. It is still increasing, but the average rate of change is getting bigger and bigger and bigger the farther to the right you go. Is h an increasing function? It is an increasing function, right? But it has a different behavior than g. In g, things were taken off. This started really revving up and started accelerating in terms of its rate of growth. But over here, with h, what's happening? Yeah, it plateaus. And I'm glad we didn't say wall because that sounds too political. All right. So, yeah, it hits this plateau. It's increasing, but, it's getting smaller and smaller and smaller in terms of the rate of increase. So it's kind of slowing down. So even though it's increasing, it's doing so at a slower and slower rate. So its average rate of change is diminishing. Now, you can apply this idea of average rate of change to other things, like running speed, and that's in problem number 32. So we've got some values here. It says, what was the man's average rate of speed between 68 and 152 seconds? So again, that's just the slope. Let's do this one by hand. Find the slope. So I want this one and this one. So let's write down those points. And so let's see. 32A. So we have points at 68 and 400. And what else? 152 and 800. So we want to find the average rate of change of his distance in that interval. So it's going to be 800 minus 400 over 152 minus 68. So 400 over, what, 84? So we're getting about 4.76. And let's take a look here. The units here are in what, meters? So the numerator will be units of meters. What's the denominator units in? Did anyone catch that? Seconds. So 4.76 meters per second. That seems reasonably fast. So what was the average rate of speed between 263 and 412 seconds? So they're asking us to do this again. I don't see a real let's see. Let's just do this one last one here. Kind of like that. So 263 went along with 1200. And let's see, 412 went along with 1600. So again, the average rate of change, 1600 minus 1200 over 412 minus 263. So 400 divided by 149. 2.68. Again, that'd be meters per second. So what's happening as he's running farther and farther? He's slowing down. You can see that graphically if you look at Desmos. I've got these points plotted for you. So let me zoom out a little bit. Shut these old graphs off. Let's see, I got one more. There we go. Let's get rid of that one. And if you turn on this table, like I said, you're going to have to zoom out considerably. So on the x-axis, let's go from 0 to 450. And then on the y-axis, go from 0 to, let's see, call it 1800. And you should be able to see all these points. I don't know, can you see it a little bit? He's slowing down, right? Kind of reminds us of that plateau that we were seeing with the previous problem. You know, I mean, you can't maintain such a fast speed forever, and we see that with his velocity. His average velocity is slowing down. I did a little something fancy here. We can fit a quadratic equation to this. And we're seeing, again, the same thing, that approximately speaking, there's a little bit of an arc in there. It's slowing down. So, okay, for homework, try 17 through 19 and 27 through 33. 7 through 19, yeah. Thank you. 7 through 19. Actually, you know what? I already sent you an email with this, didn't I? Good on me. All right. Have a good one.